Hello everyone. Our project is called Autonomous Minefield Navigation. My name is Vidhi Patel and I worked on the project together with Josiah and Bengala. The purpose of our project is to compare two well-known path planning algorithms, A-star and Dijkstra's algorithm, to determine which one provides a better balance between safety and efficiency when navigating a simulated minefield using V-boards. Um, Autonomous navigation is one of the most important challenges in robotics, especially in environments that are dangerous for humans. In our project, we focus on a mindful scenario where a robot must travel from a starting point to a destination while avoiding mines and other obstacles. The robot needs to plan a path that is not only safe but also efficient. This problem is important because autonomous robots are increasingly being used in hazardous environments where sending people could be risky. Examples include military operations, disaster response, and industrial inspection in unsafe areas. Our motivation is to determine which path planning algorithm performs better in these situations. By comparing A-star and Dijkstra's algorithm under the same simulated conditions, we hope to identify which algorithm provides the best balance between navigation safety and computational efficiency. Our research is centered around one main question, which path planning algorithm A-star or Dijkstra's algorithm provides the best balance between navigation and safety efficiency. Based on the previous research, our hypothesis is that A-star will perform better because it uses a heuristic to guide the search toward the goal, and this allows it to explore fewer unnecessary nodes and reducing computation time while still finding an optimal path. However, we expect both algorithms to successfully reach the destination when a safe path exists. The main contribution of our project is a direct comparison of these two algorithms under identical simulation conditions. Instead of developing a new navigation algorithm, we evaluate their performance using several metrics, including success rate, mine collision, path length, travel time, and computational efficiency. I'll now hand it over to my teammate who will explain the AI methods used in our project.
In this project, we compared two well-established path planning algorithms, A-star and Dijkstra algorithm, to determine which provides a better balance between navigation safety and computational efficiency for autonomous minefield navigation. Both algorithms are designed to find the shortest collision-free path from the robot's starting position to the goal. Dijkstra algorithm searches by expanding nodes based only on the accumulated travel cost from the starting point. Because it has no information about where the goal is located, it explores the environment uniformly in all directions, which often results in a larger search space and higher computational costs. In contrast, A-star extends Dijkstra by incorporating a heuristic function. In our project, the Manhattan distance, which estimates how far each node is from the goal, this heuristic guides the search towards the destination, allowing A-star to ignore many unnecessary nodes while still guaranteeing the optimal path.
Okay, now let's talk through the system methodology. The whole system actually works because there are really three pieces working together, which is perception, planning, and control. We started by modeling the minefield as the two-dimensional grid, and each cell on the grid is one of five types. A start cell where the robot begins, a goal cell where it needs to reach, a mine cell, obstacle cells that are both non-traversable and represent danger zones, and empty cells that the robot can freely move through. Movement is restricted to four directions, so that's up, down, left, and right. And there's no diagonals, and every single step costs the same amount, which just keeps the comparison between our two algorithms fair and controlled. The first piece of our system is perception, so this is how the robot actually senses the danger around it. In our Python simulation, this is straightforward. Before the robot moves into any cell, we check whether that cell is a mine or an obstacle, but we didn't stop at the abstract simulation. We also implemented this in the Weebot software. So which was a real physics 3D simulator. We weren't unfortunately able to use VX Code VR because the license expired for the world. So we decided to use this instead. And we used an EPUC robot, which was equipped with 8 infrared proximity sensors arranged around its body. So those sensors gave the robot real physical obstacle detection. And it's not just a lookup in a data structure. So the second piece was planning, and this is where A-star and Dijkstra's algorithm can come in. Both algorithms are given the exact same map, the exact same start and goal, and each one computes what it believes is the optimal path. And the third piece is control, so actually executing that path. This turned out to be more interesting than we expected because early on we tried having the robot estimate its movement just purely based on counting rail rotations, but that approach slowly drifted the robot off course for like the longer paths. So instead, we built a closed loop control system where the robot continuously checks its position and heading and checking those it corrects itself towards the target the whole time that it's moving. So after putting all that together, we got our system flow shown here. So we load the Minefield, initialize the robot, choose an algorithm, compute the path, then we have the robot execute it, and finally we collected our six evaluation metrics. So, with the system architecture covered, we'll now talk about how we actually designed our experiments, because the setup here really matters for making sure our comparison is fair. So, we tested three difficulty levels. The first is easy, an 8 by 8 grid that's mostly open space with just a handful of scattered obstacles. And then the second one was the medium course. So, it was a 15 by 13 grid that we purposely built as a true maze, complete with dead ends and branching paths and then using a recursive maze generation approach. And the third one is the hard one. So that one was a 16 by 16 grid, and that was our like most largest complex environment. So the single most important design decision we made was this. For any given difficulty level, so both A-star and Dijkstra, they both always run on the exact same map. Same start position, same goal position, same obstacle positions, mines, all of that, every single time it was the same. And that might sound obvious, but the reason it was important is if the algorithms ran on different maps, we'd have no way of knowing whether a performance difference came from the algorithm itself or just from one map happening to be easier. So by holding the environments constantly the same, any difference we had to measure has to come from the algorithm itself. And then in terms of scale, we didn't just run each combination once. In our Python simulation, we ran 30 separate trials for every combination, as well as the difficulty. So that's two algorithms times three difficulty levels times 30 trials. So that was 180 total trials. And running that many trials matters because it just lets us average out any small timing noise, especially for metrics like computation time. And it gave us a statistically like solid data instead of relying on single like lucky run or maybe like an unlucky run. But we also wanted to go beyond just the purely abstract simulation. So for each of the six algorithm and difficulty combinations, we also ran a validation test inside Weebots. Um, so that gave us a way to confirm that whatever we found in the grid model actually holds up when a physical robot has to execute it in a more realistic setting. Okay, so now we'll go over our experimental results. So across all 180 trials in our Python simulation, both A-star and Dijkstra achieved a perfect 100% success rate. So this just means that there were zero collisions on every single difficulty level every single time. And that's an important result on its own as well, because that means whichever algorithm you choose, you're not sacrificing safety, and the robot never entered a mine or ran into an obstacle in any of our tests. We also found that both algorithms produced identical optimal path in every trial. So 14 steps on the easy map, 26 steps on the medium map, and then 30 steps on the hard map. And this actually makes complete sense mathematically as well, because when you think about it, both A-star and Dijkstra are optimal search algorithms. So on every grid where each step costs the same amount, they're bound to find the shortest path that exists. And there's no scenario in our setup where one algorithm finds a genuinely shorter or safer path than the other one. What we think is one of the more important parts of our results, though, is the Weebots validation. So in our 3D environment, the results matched our Python simulation as well. The same number of nodes were explored, the same path lengths, and beyond that, in every single 3D run, the robot's final position ended up within 4 millimeters of the true goal location. So that's a very consistent result, and it tells us that our findings aren't just because of a simplified model, but they also hold up when an actually physically simulated robot with real sensors in a real closed loop has to execute the plan in a real world environment. So just to summarize this slide, both algorithms are equally safe, equally reliable, and produce equally good paths. So what we get into next is about how much work each algorithm has to do to get there. So now we'll do the comparison between the algorithms, and I think this is the most important part of our project because this is where the real difference between A star and Dijkstra shows up. So as we explained just now, both algorithms tie on safety and path length every time. So the real question becomes how much searching does each algorithm actually have to do to find that path? And that's measured by our nodes explored metric. So essentially, how many grid cells did the algorithm have to look at before it found the goal? So on the easy map, there's basically no difference at all. Both algorithms explored exactly 59 nodes. And that actually makes sense because the easy map is the most open space map. There isn't much for A star to take advantage of. Almost every direction leads roughly towards the same goal. But once we move to the medium map, this is our true maze map. So it has the dead end corridors and things like that. So for this one, A star explored only 60 nodes, while Dijkstra explored 84. So that's about a 40% reduction in search effort. And on the hard map, A-star explored 66 nodes compared to Dijkstra's 100. So that's roughly a 34% reduction. So the pattern here was very clear as we explored this. The gap between the two grows as the environment becomes more maze-like and more complex. And the reason comes down to how each algorithm actually searches. So Dijkstra has no idea where the goal is. Its whole thing is to expand outward from the start in every direction pretty much equally. So when it hits a dead end, it has no way of knowing that in advance. It has to fully explore it. But A-star, on the other hand, uses an approach that's a straight line uh, to the goal. So it prioritizes exploring cells that are actually moving it closer to the destination. So that lets it skip over branches that are clearly leading in the wrong direction without ever sacrificing finding the true optimal path. So for in summary, the takeaway is that A star gives you the exact same safety and the exact same like path quality as Dijkstra, but with less computational overhead. And the advantage becomes more valuable as the size and complexity of the environment increases.
Our results show that both A-star and Dijkstra algorithm achieved a 100% navigation success rate, found the shortest path, and completed all trials without collisions. This confirms that both algorithms are reliable for autonomous minefield navigation. The main difference was efficiency. A-star explores significantly fewer nodes than Dijkstra because it uses a heuristic to guide a search towards the goal. This makes A-star more computationally efficient, especially in complex environments. During implementation, we faced challenges such as migrating to webbots, correcting the well-encoded drift using a closed-loop control, and redesigning the medium maze to better highlight the performance difference between the two algorithms. Overall, these improvements strengthen the accuracy and reliability of our results. In conclusion, this project successfully compared A-star and Dijkstra algorithm for autonomous minefield navigation under identical simulation conditions. Both algorithms achieved 100% navigation success, avoided all collisions, and consistently found the shortest path to the destination. These results demonstrate that both algorithms are reliable and effective for static autonomous navigation tasks. However, A-star proved to be more efficient algorithm because it explored fewer nodes while maintaining the same path quality. Its heuristic guided search reduced the amount of computation required, especially as the environment became more complex, making it the preferred choice for large-scale robotic navigation. Looking ahead, future work will focus on extending this project to dynamic environments with moving obstacles, comparing these classical algorithms with AI techniques such as reinforcement learning and multiple ANFIS, integrating SLAM for real-time mapping and localization, and implementing the system on a physical mobile robot equipped with real sensors. These improvements would make the navigation system more robust and closer to real-world autonomous robotic applications.